Okay, so now we're going to start section 1.3, which is on the Hamiltonian circuits and the traveling salesman problem. In the last section, we considered optimizing a walking route for a postal carrier. How is this different than the requirements of a package delivery driver? While the postal carrier needed to walk down every street or an edge to deliver the mail, the package delivery driver instead needs to visit every one of a set of delivery locations. Instead of looking for a circuit that covers every edge once, the package driver is interested in a circuit that visits every vertex once. Okay, and this should make sense because if you have delivery drivers, let's say somebody who's delivering appliances to be installed, they have a certain number of stops for the day, and they want to be obviously stop at each one of those stops only once, right? They don't want to stop at a place and then leave and then have to come back, right? So it's the locations that are the important thing, not the streets or the paths, that the edges in this case. Okay. So the definition of a circuit, right? So in this case, Hamiltonian circuits and path. Okay, so a Hamiltonian circuit is a circuit that visits every vertex once with no repeats. So unlike the Euclidean, the Euler circuit, where we were interested in a circuit that visits each edge only once, right? So in this case, the Hamiltonian circuit visits every vertex only once with no repeats. Okay. Now, being a circuit, it must start and end with the same vertex, obviously. Now, a Hamiltonian path also visits every vertex only once, but remember, the beginning and ending vertex are not the same. Okay. They do not have to be the same. Now, Hamiltonian circuits are named after William Rowan Hamilton, who studied them in the 1800s. So let's look at example 11. Okay, so it says one Hamiltonian circuit is shown in the graph below. There are several other Hamiltonian circuits possible on this graph. Notice that the circuit only has to visit every vertex once. It does not need to use every edge, right? So it doesn't have to use every edge, but it has to go to each vertex once. So in this case here, they started with vertex A. So in this circuit, could be notated by the sequence of vertices visited, starting and ending at the same vertex. So we could start with A, right? And so one of the circuit could have been A, right? And then to B, F, G, C, D, H, M, L, K, J, E, and then A again. Okay. Now, unlike Euler circuits, there is no nice theorem that allows us to instantly determine whether or not a Hamiltonian circuit exists for all graphs. However, there is one observation that is quite useful in narrowing our search. If there is a Hamiltonian circuit, then that circuit must place exactly two edges on each vertex. So let me repeat that. If there is a Hamiltonian circuit, if there exists a Hamiltonian circuit, then that circuit must place exactly two edges on each vertex. Okay. This means that if there is a vertex of degree 2, then both of the edges that have this vertex as an endpoint must be used in any Hamiltonian circuit. So moreover, if there is a vertex of degree 1, then a Hamiltonian circuit is impossible, although there still may be a Hamiltonian path. Okay? So, let's look at example 12 so we can see what's going on here. Okay, so it says, does a Hamiltonian circuit exist on the path below? So let's look at this. So if we look at the paths, right? Vertex A and B, for example, we have exactly what? Must have exactly two edges on each vertex. But if you look at this one, right away, we could see that, look, E only has one edge, right? So remember, from the last statement here, right here, we know that a Hamiltonian circuit is impossible because since this only has a degree 1, right, we can't go back to E. If we start with E, we can't go back to E without first hitting at least one vertex more than once, namely C, right? And we can't start with any other vertex because as soon as we hit E, we're going to have to hit C twice. So that's why it's impossible. Okay, but we can have a path though, right? Because we could start with B, right? And we could go to A, and then D, C, and then E. Okay? Okay, so this graph cannot have a Hamiltonian circuit because degree E is equal to 1. From the picture, we see that once we travel to vertex E, there's no way to leave without returning to C, like which is what I was saying, right? You're going to end up hitting C twice, regardless of what you decide to do. So there's no possibility of a Hamiltonian circuit. However, if we start with vertex E, we can find several Hamiltonian paths. And I've named one up here, right? But we have a couple others too that we can use. Okay? With Hamiltonian circuits, our focus will not be on existence, but on the question of optimization. That is, if we are given a graph where the edges have weights, how can we find the optimal Hamiltonian circuit, the one with the lowest total weight? Okay, this problem is called the traveling salesman problem, or what we call TSP, because the question can be framed like this. Suppose a salesman needs to give sales pitches in 4 cities. He looks up the airfares between each city and puts the cost in a graph. In what order should he travel to visit each city once, then return home with the lowest cost? Okay. The answer to this question of how to find the lowest cost Hamiltonian circuit, we will consider some possible approaches. The first option that might come to mind is just try all different possible circuits. This is called the brute force algorithm, or what we call the exhaustive search. Okay, and so in order to find that, it's basically we just try to find every possible combination, try all of the different combinations, and then just choose the one that has the lowest cost. So it's step 1 for the brute force algorithm. Step 1 is to list all possible Hamiltonian circuits. And then step 2, find the length of each circuit by adding the edge weights. And then step 3, select the circuit with the minimum or minimal total weight. Okay, so that's just by brute force. Okay. So if we look at example 3, right? So if we look at this, if we want to apply the brute force algorithm to this graph here, then all we would do is we would try to find all the possible Hamiltonian circuits. So what are the possible Hamiltonian circuits? We can list them out. Okay, with this one here, we could go, there's only so many, right? So all the possible Hamiltonian circuits are listed below. So we can go A, B, C, D, A. We can go A, B, and then C, D, A. Okay, or we can go A, B, D, C, A. Or we can go A, C, B, D, A. Now keep in mind, any other combinations that we can come up with are just repeats or reverse order of the other one. So it says note down here, says these are the unique circuits on this path. All other possible circuits are the reverse of the listed ones, or they start at a different vertex, but they result in the same weights. Okay? So by this case, we find that the optimal circuit is this one right here. That adds up to 23. Okay? Now, the brute force algorithm is optimal. It will always produce the Hamiltonian circuit with the minimum weight, but is it efficient? Now, to answer that question, we need to consider how many Hamiltonian circuits a graph could have. For simplicity, let's look at the worst case possibility where every vertex is connected to every other vertex. This is called a complete graph, right? So we have a complete graph. Now, suppose we had a complete graph with 5 vertices, like the air travel graph above. So let's go back to this one here. So let's consider this graph right here. Okay, so we've got 5 locations that the traveling salesman has to travel to. Now, suppose we had to complete the graph with 5 vertices. Now it says from Seattle, there are 4 cities. Okay, so let's say this is our home base, Seattle. Okay, so from there, we have 4 cities, right? So we're going to travel to one of these 4 cities. So if we travel to LA, then once we travel to LA, then we've got 3 other cities to choose from. And then if we choose to go to Dallas, then from there, we've got the 2 other cities left to choose from. And then if we choose to go to Chicago, then that leaves the last one to go to is going to be Atlanta before returning home, right? Because we obviously have to get back home. Okay, so that's one option. And then so each branch of this tree leads to another option, right? Another path of going home. So in this case here, if we look at all of the different routes, right? How many different options are there? How many different ways can we complete this? Well, there's going to be 24 routes before returning home. Now, for 6 cities, if we just add a city, it jumps up to 120 routes. So you can see how this will get out of hand very quickly. And so in order to find the total possible circuits, we use this formula, n minus 1 factorial. Okay? Now, but here's the thing. For a complete graph with n vertices, the total is going to be what? N minus 1 factorial Hamiltonian circuits. Now, here's the thing. Half of these are duplicates, right? In reverse order. So they're actually going to be n minus 1 factorial divided by 2. unique circuits. Okay, and so the factorial key just means this. The factorial symbol just means that we're going to take that number, whatever this n minus 1 is, and we're going to multiply it by every number, every unique integer less than that. So in this case here, we go n minus 1, n minus 2, n minus 3, all the way down to 1. So if we have 3 factorial, right? So 3 factorial is equal to 3, right, times 2 times 1, which equals 6. Okay, so the number of possible circuits, unique circuits, is going to be n minus 1 factorial divided by 2. Okay. Okay, so let's look at this. Example 1. Let's look at example 1, or example 14, I mean. It says, how many circuits would a complete graph with 8 vertices have? Well, if we use again the formula 8 minus 1 factorial, okay, what do we get? Well, that's 7 factorial, which is equal to this, which is equal to 5,040 possible Hamiltonian circuits, but half of these are going to be duplicates. So as far as duplicates of other circuits, but in reverse order, this is what we'll have. We'll end up with 2,520 unique routes. Okay? Now, while this is a lot, it doesn't seem unreasonably huge, but let's consider what happens as the number of cities increases, right? Look at this. I mean, by the time you get to 20 cities, you're looking at a huge number of unique routes. That would be just impossible to do. Okay, so as you can see, the number of circuits is growing extremely quickly. If a computer looked at 1 billion circuits a second, 1 billion circuits each second, it would still take almost 2 years to examine all the possible circuits with only 20 cities. Certainly, brute force is not an efficient algorithm. Unfortunately, no one has found an efficient and optimal algorithm to solve the traveling salesman algorithm, or the problem, traveling salesman problem, yet. And it is very unlikely anyone ever will. Since it is not practical to use brute force to solve the problem, we turn instead to heuristic algorithms. And those are efficient algorithms that give approximate solutions. In other words, heuristic algorithms are fast, but may or may not produce the optimal circuit. So the first one that we're going to talk about is called the nearest neighbor algorithm. Okay, the nearest neighbor algorithm works like this. We first select a starting point, any starting point. That's step number 1. Step number 2, we move to the nearest unvisited vertex, the edge with the smallest weight. Okay, that's what we're going to use. We're going to use this one with the smallest weight. So nearest in this case is based on the weight. Okay, it could be the nearest location if we're talking about geographical, but it could be a cost, right? So the way we're going to use is we're going to move to the nearest unvisited vertex by looking at the weight of each edge. And then finally, 3, we're going to repeat this process until the circuit is complete. Okay, so this is what we do for the nearest neighbor algorithm. Okay, so let's do an example. Okay. And here's the example. It says, consider the earlier graph. So here's our graph that we were talking about earlier and shown to the right. So we're going to start with vertex A and we're going to do the nearest neighbor. So if we look at A, so let's start with A, right? Oops. So we're going to start with A. Okay. So the nearest neighbor, we're looking at the path. So what are all the paths connected to A? So we have A to B, A to D, and A to C. Now, if we go, obviously the nearest one, because is going to be A to D, right? So let's do that. So now we've got A to D. Now, if we look at this, we look at the nearest neighbor here. And so obviously the one with the lowest weight is going to be D to C. Okay, so let's go to D to C. Okay, now from C, we can't go to A because we already visited A. So the nearest unvisited one is going to be B. So we have to go to B. And then we're going to go back to A. So the path is going to be A to D, D to C, C to B, B to back to A. So if we count up those weights, we get 1, 9, 22, 26, right? So we get 26 as our total. Now, we ended up finding actually the worst, right? Remember? So if we go back up here, remember when we added up the brute force, right? 23, but we ended up finding the worst one by using the nearest neighbor algorithm. Okay, so what happened? Unfortunately, while it is very easy to implement, the nearest neighbor algorithm is greedy. It's a greedy algorithm, meaning it only looks at the immediate decision without considering the consequences in the future. In this case, following edge AD forced us to use the very expensive edge later, which was BC. Now, if we were looking forward, if we were looking ahead, we could have chosen maybe a more expensive, quote unquote, a more expensive route in the beginning to avoid the more expensive route at the end. Okay, but again, this is planning, right? But this is how the nearest neighbor algorithm works, right? It's very easy, but it's not going to guarantee us the optimal path each time. And in this case, it gave us the worst one. All right, we'll stop there and we'll come back and we'll do another example.